So now we're going to look at this thing called quadratic approximation, and we'll first recall what linear approximation looks like in functions of two variables. So recall that the tangent plane, or the linear approximation of this function, is f of x naught y naught, which I'm going to abbreviate p, plus the partial with respect to x plus the partial with respect to x at p plus the partial with respect to y at p. And I'm just abbreviating p and I'm using shorthand. P is x naught y naught. Okay, so the quadratic approximation adds three terms. So we'll call it q of xy. It's going to be the linear approximation plus fxx at p over 2 x minus x naught squared plus fxy at p times x minus x naught y minus y naught plus fyy at p over 2 y minus y naught squared. Notice this one doesn't get divided by 2, but these two do. So the mixed partials, there's two of them, and so they're being added together and turned into one term. So there's three additional terms to the linear approximation. All right, so let's do an example. So let's find q of xy at the point 0, 0. That's my p. Given this function cosine 2x plus y minus cosine x plus 2y. Okay, so let's compute the derivative with respect to x. So cosine is going to become negative sine 2x plus y times 2. And then once again, cosine is going to become negative sine, so this will be plus sine x plus 2y, and then there won't be a 2 out here because the coefficient of x is 1. And if we evaluate this at the point, we're going to get, well, 0, sine of 0, and sine of 0, those are 0, so this is 0. That's nice. And the derivative with respect to y is going to be really similar, except you're not going to get a 2 because the coefficient of y is 1 here, and you will get a 2 here. And the derivative with respect to y at the point p is also 0. Now we're ready to compute our mixed partials, our second order partial, excuse me. So the derivative of this thing with respect to x, well, you take the derivative of sine, you get cosine. So this is negative cosine 2x plus y. You get another 2 out, so that becomes 4 outside. And the derivative of the sine is cosine again, so we'll get fxx at the point p is going to be negative 1 times 4 plus 1, which is negative 3. Now we compute our mixed partial. So we're going to take the y or the x and compute the other derivative. Let's use the x, so we'll take this x and we'll take the derivative with respect to y. If we take the derivative with respect to y, we're going to get negative cosine 2x plus y times 2. There's a 1 that comes out, doesn't change anything. And then plus cosine x plus 2y times 2. And if we put in p here, put in 0, we'll get negative 2 plus 2, which is 0. last one, and I'm just going to write this really quickly. It's going to be negative cosine 2x plus y plus cosine x plus 2y times 4. And if we put in our point, we'll get negative 1 plus 4, which is 3. Okay, so now we're ready for our quadratic approximation. Qxy is going to be, well, it's going to be the function evaluated at 0. So f of 0, and I didn't do that, so let me do that right here. So f of 0, or f of p, is put 0 into this function, and I get 1 minus 1, which is 0. So we'll get 0 plus 0 times x minus 0 plus 0 times y minus 0. This is the linear approximation. It's all zeros. And then we add the quadratic terms. So we get negative 3 over 2 x minus 0 squared plus 0 times x minus 0, y minus 0, plus 3 over 2 y minus 0 squared. So my quadratic approximation simplified is negative 3 halves x squared plus 3 halves y squared. So here's the graph of the original function, and I want us to see that this quadratic approximation really is telling us what this function looks like near the origin. So this is x here, and this is y. And if we drew this quadratic approximation, we'd get a saddle. It would look like this. And you can see that this function indeed looks like this saddle at points near the origin. It has that saddle-like feature. Okay, I want to do one more example. So I want to find the quadratic approximation at the origin when we have this function e to the negative x squared minus y squared, which is this bell-shaped curve in 3D. And I'm not going to go through all the math here. I will just give you the partials, second order partials. So you can check this on your own, that the second partial with respect to x is this. Second order partial that's mixed is this. And the second order partial with respect to y, well, it's going to be a lot like the one for x, just with x and y flipped because it's symmetric. And if you work this out, put in 0, 0 at all these partials, and in the first order partials, you should get that the quadratic approximation is 1 minus x squared minus y squared. And once again, I want to draw this on here. So 1 is here, that's the top, and you can see that this does look like a paraboloid locally, which is what this is. This is a paraboloid that's downward facing and centered with vertex at z coordinate 1.